Hello everyone. Welcome to the ILTA Physics Problem Solving Online lecture. Today, we're going to solve some problems together regarding uniform motion. As the name suggests, uniform motion is when an object moves at a constant speed. As you can see in the diagram below, it's like a car driving from left to right at a steady velocity. In other words, uniform motion means the object moves at a consistent pace the whole time, it doesn't speed up, and it doesn't slow down to a stop. Since the motion itself is relatively simple, the problems related to it are also very straightforward. If you know the speed and the time of a moving object, you can find the distance traveled just by multiplying the two. Now let's briefly summarize the theory behind uniform motion. In our previous theory lecture, we defined uniform motion as the movement of an object at the same speed, meaning a constant velocity. It looks just like the motion in the diagram below. Because this type of motion is so simple, to get straight to the point, you only need one formula for problem solving, as shown at the bottom. In kinematic equations, the final position of an object is calculated as the sum of its initial position and the distance traveled. Here, the distance traveled, or the displacement, can be calculated by multiplying velocity and time. With just this formula, you can solve most uniform motion problems fortunately. So let's look at the physical characteristics and ways to express uniform motion one more time. First, let's explain uniform motion in terms of displacement. The definition is that the distance traveled, the displacement, is the same during consecutive, equal time intervals. Second, if we explain uniform motion from the perspective of velocity, it is motion at a constant velocity. To be precise, constant velocity means not only the same magnitude, but also the same direction. In other words, velocity is a vector quantity, so having the same velocity means both the direction and the magnitude are identical. Third is the visual representation of uniform motion. A motion diagram for uniform motion can be shown as dots marked at equal intervals, with velocity vectors that have the same magnitude and direction. Now, let's express uniform motion in a more physics-oriented way. As a fourth method, if we represent uniform motion on a position-time graph, it appears as a straight line with a constant slope. This shows how the position changes over time, and the rate of change is the velocity. Finally, here is the graph showing the relationship between time and velocity. Even as time passes, the velocity stays constant. In this graph, the area, which is velocity times time, represents the change in position or the displacement. The quantitative problem solving for this kind of uniform motion eventually boils down to the following kinematic equation. As I mentioned before, the final position of an object is the result of adding the displacement, velocity times time, to the initial position. At this point, the velocity of uniform motion, by definition, is the displacement divided by the time interval, and this value stays as a constant. If you don't quite get the physical characteristics or the representations I just explained, please go back to my theory lecture first. Make sure you understand it clearly before returning to these problems. All right, let's start solving some uniform motion problems. Question 11 asks who arrives first and by how much. When Alan and Beth leave for San Francisco, which is 400 miles away, at different starting times and different speeds. Since both people moved at a constant speed, this is a simple uniform motion problem. One thing to consider in this problem is the final arrival time. You need to calculate the travel time first, and then factor in the different starting times to find the arrival time. So, let's first calculate the time it took for each person to travel. The formula is very simple. Final position equals initial position plus velocity times time. First, let's look at Alan. If we call his travel time T, A, and plug it into the formula, the final position is 400 miles and the initial position is 0. Since the speed is 50 miles per hour, we set it up like this. 400 equals 0 plus 50 times TA. Solving this, it takes Alan 8 hours to travel 400 miles. Since Alan's departure time was 8 a.m., adding 8 hours of travel means he arrives at 4 p.m. Something to think about here is the initial position. The problem says they started in Los Angeles and arrived in San Francisco. If we set the starting point as the origin, meaning the initial position is 0, then the final position becomes 400. Generally, it's very helpful to set the initial position of an object as the origin of your coordinate system. The second thing to consider is the units given in the problem. Usually, it's standard to use SI units like meters and seconds. However, in this case, since all the conditions are given in miles and hours, it's perfectly fine to calculate using those units. Make sure to practice applying units consistently based on the problem type and conditions. Now let's get back to the problem. If we calculate for Beth the same way we did for Alan, her travel time is 6.67 hours. For convenience, if we express this in minutes, it's 6 hours and 40 minutes. So, her final arrival time is 3:40 p.m., considering her 9 a.m. departure. Even though she started an hour later, she arrived earlier because she was going faster. So, Beth arrives in San Francisco first, and the time difference is 20 minutes, which is 1200 seconds. Even though the formula used is very simple, please take your time to think it through and understand it. Question 14 describes two runners running 8 kilometers at different constant speeds. The question asks for the distance gap between the two runners at the moment the faster runner crosses the finish line. You can probably imagine the scene in your head. If you can read this problem and draw a diagram like the one below, you've basically solved most of it. First, both runners are at the same starting line. Then, at the moment the faster runner hits the finish line, the slower runner is trailing behind. The goal is to calculate that distance gap. Let's set up a strategy based on that explanation. First, calculate the time it takes for the faster runner to reach the finish line. Then, calculate how far the slower runner traveled during that same time interval. Finally, subtract the slower runner's distance from the total distance to find the gap between them. Now, let's do the quantitative calculation using the formula. We only need one formula. Final position equals initial position plus velocity times time. First, for the faster runner's arrival time, they ran 8 kilometers at 14 kilometers per hour, so the time is 0.57 hours. There's no need to convert this to minutes here. Since the speed unit is given in kilometers per hour, you can just calculate using hours. You'll naturally pick up these kinds of tips as you practice more problems. Next, let's calculate the distance the slower runner traveled. We'll apply the same formula, but be careful to use the correct values for each runner. When a problem involves two or more moving objects, it's important to practice identifying and separating the physical quantities for each one. Using the formula, the distance traveled by the slower runner is 6.27 kilometers. Therefore, the distance gap between the two runners is 1.73 kilometers. The calculation for uniform motion is very simple. Please practice applying this relationship correctly according to the conditions of the problem. That's it for today's lecture. Great job, everyone. See you next time.